Okay, let's go with the second video on generalized inverses. There is a special case uh, for P1 and P2. If you remember the previous theorem, uh, uh, that there was a relation between two matrices, and we could construct a relation between the generalized inverses of those two matrices. Here we have a very interesting special case. Suppose that B, P1 and P2 are defined as follows. Then for any A, there exists two non-singular matrices P1, P2, such that we have this equality here. And the rank of A is equal to R. Here, it is a block diagonal matrix. On the diagonal entries, we have the identity matrix and a zero matrix. So these zero matrices are matrices that all elements are equal to zero. In order to construct the generalized inverse of B, suppose that D is equal to this matrix with this block structure. X is an R by R matrix, U R by M minus R, V n minus R by R, and W n minus R by M minus R. Then it follows, remember, we want to find the generalized inverse of B. So we pre-multiply, post-multiply by D, pre-multiply, post-multiply D by B. So we have B dB. If I assume B is equal to this block structure, then we have this structure pre-multiplied by D. This is D actually, and then the matrix again. And if I compute the multiplication, for instance, if I multiply these elements with these elements and sum up with each other, again these elements with these elements and sum up with each other, then I have this structure. On left hand side, right hand side, I bring this guy here, and if I multiply it, the first element is x multiplied by r plus u multiplied by 0, which is equal to x. So B dB is equal to this matrix. But if D wants to be the generalized inverse of B, it must be equal to B. And we have already assumed that B has this structure, block diagonal structure. So we can conclude that a necessary and sufficient condition for D to be generalized inverse of B is that X is equal to identity matrix of dimension R. And so in general, we can say the generalized inverse of B has this specific structure, which the first block is identity matrix, and these U, V, W matrices can be arbitrary matrices. Now let's go with other special cases. First of all, we have a very important result that shows that there always exists at least one generalized inverse for any matrix. And as I said in the previous video, it is not the generalized inverse is not always unique, and a matrix can have an infinite number of generalized inverses. Now we have a interesting special case. If matrix A is non-singular, then this is the definition, better say a theorem about the generalized inverse A star. Better say A star is generalized inverse of A is if A star A is equal to A. I pre-multiply, post-multiply both sides by A inverse because A is non-singular. So from the generalized inverse, I can write this matrix in the middle as A, and then we have A inverse A inverse. So we can assume that generalized inverse of A, which is in the middle, is actually equal to A inverse. because A inverse times A is equal to identity, and it is equal to A inverse. So we can assume that the generalized inverse is equal to A inverse. And this is very important. This is an important result. And you see, as I started in the previous video, when you have such an equation and x prime x is invertible. When you say invertible, it means that it is rank efficient and is a non-singular matrix. So you can invert it, and the generalized inverse is actually the inverse of this matrix, and you can then easily find the estimate of beta, which is equal to this expression. Here xt is the transpose of x. And actually this result is important in order to conclude this least square theory schematic. Another thing which is very important is the uniqueness of the generalized inverse, or the theory behind uniqueness of a generalized inverse. In some cases, or better say in one case, which we call it Moore-Penrose Inverse, and it's defined by Penrose and Moore simultaneously, we can find a unique generalized inverse. We will say that a matrix C is a Moore-Penrose inverse, which is unique if it satisfies these four conditions. So if we have these four conditions, then we can say that C is a unique generalized inverse of A, or better say it's a Moore-Penrose inverse of A. So if you're provided with the Moore-Penrose inverse, then you're confident that it's a unique generalized inverse, and there is no other generalized inverse. Another result, if A is n by n and symmetrical, A star is a generalized inverse of A, and we can conclude that this happens. Now you can transpose both sides. If I transpose this side, then I have A prime, A star prime, A prime, and right hand side is A prime. So since A is a symmetrical matrix, instead of A star A transpose, I can write A here. The transpose is denoted by this hash here. So A star is equal to A. So I can write this expression as A star transpose A equal to A, and then you can conclude that A star transpose is again a generalized inverse. So A star is not necessarily symmetrical, and A star transpose is a generalized inverse of A. So in case of a symmetrical one, we will have this transpose as the generalized inverse, or better say we have two generalized inverses. Once again, remember that being symmetric doesn't conclude that it is of full rank. We must be careful a little bit about it. Another one is this number 6. It is always possible to choose a symmetrical generalized inverse for a symmetrical matrix A, and you can easily obtain it by adding the transpose of a generalized inverse and make it half. And it is easy to see that it is generalized inverse of A. Remember, once again, you will say a matrix M is generalized inverse of A if A is equal to A. Now I want to say that this guy is the generalized inverse of A. So I can pre-multiply by A, like here, post-multiply by A, and see what I get. If I get the identity to A or equality to A, then I will say, okay, this is the generalized inverse. So I pre-multiply by A, post-multiply by A. This is a factor which comes out. This factor is, it can come out from the multiplication. So if I multiply, then I have half A star and half A star transpose, which I can write it as, if I want to show it by another pen, then I can write it this way. So I have half A star, and remember this A from this side, this summation comes here. Once again, half A star transpose A. First of all, A star is generalized inverse of A, so this guy is equal to half A. Here in number 5, we learned that the A star prime is also a generalized inverse of A, so I can write this guy as the generalized inverse of A and include half. So we have half A plus half A, which is equal to A. It shows that this half A star plus A star prime is the generalized inverse of A, and it's a symmetrical matrix. So you can always find a symmetrical generalized matrix. The other result, which is the most important result and opens a broad view in front of your eyes about the linear equations, is this result, which also shows that the generalized inverse is not always unique. If you remember from the previous video, I said I promised to show that you can always write a specific structure to get different generalized inverses. Now here we discuss about it. In the case that the matrix A n by n is assumed, it follows that A star A is idempotent, and it's easy to see. Once again, a matrix B is idempotent is B2 is equal to B. Okay, so I want to show that this matrix is idempotent. I will write it A star A times A star A. From generalized inverse, I can write this guy as, but I better write it this way, sorry. I can write this guy as A, because A star is generalized inverse. So the resultant matrix is equal to A star A, and you will see A star A power 2 is equal to A star A, so it's an idempotent matrix. And that the columns of I minus A star A generate a vector space orthogonal to the rows of A. What does it mean? Remember the orthogonality notion. You say two matrices are orthogonal if the inner product is equal to 0. So if you, before I show this, since A star A is idempotent, I minus A star A is also idempotent. This is one thing. Now I want to show that these are actually this matrix generate a vector space orthogonal to the rows of A. When you say orthogonal to the rows, it means that you must start from the rows. It means you must write A on the left and then multiply with I minus A star A. This is important. So it shows that this matrix construct a vector space to the rows of A. Now let's do the multiplication. We have A minus A star A. According to the definition of generalized inverse, we can say A star. Since A star is generalized inverse of A, I can write the second one as A, and it is then equal to 0. So it makes an orthogonal vector space orthogonal to the rows of A. Then we can conclude that the general solution of the system Ax equal to 0 is given by this formula. This is an important fact, and it comes actually from the generalized inverse of this guy. So here we showed that it is equal to 0, and from being 0, I can write x as this formula. And this z can be any arbitrary element. Now let's go to the formula or better say the relation, the relation here. If you recall from the common notation of regression modeling, then we have y equal to x beta. I want to show that the estimator for beta, which is beta hat, has a specific structure. Before going to this part, let's start from this guy. Here, ax equal to y, we can easily find the x as the generalized inverse of a multiplied by y. Write it this way. We can write ax minus y equal to 0. According to this specific structure, if I can write this expression here, or better said this equality, in the form of a matrix multiplied by a vector equal to 0, then I can obtain x by this formula here. Now let's do a further step. I can write this here. I can write it a star. Let's do it here. Let's do it let's here. So we have ax minus y equal to 0. Also remember, when a star is the generalized inverse, we have a star a equal to a. So here, instead of the identity matrix, I can write a star. So from ax minus y equal to 0, we can say, better write it, ax minus a star y equal to 0. Then our factor matrix, prefactor matrix A, here x minus a star y equal to 0. Put this guy as something like R. From above, when ax equal to 0, you can easily from ax equal to 0, you can say, okay, x is equal to I minus the generalized inverse of this matrix times z, an arbitrary z. So here I can say, okay, r is equal to 0, so r is equal to I minus a star az. So I can conclude that r here is equal to I minus a star az. Now let's replace r. So we have x minus a star y equal to I minus a star a, sorry for my bad handwriting, z. And then we can finally conclude that x is equal to a star y plus I minus a star a z. And it is actually a general solution to this equation. And that is the thing that we already discussed in the previous video for all the solutions. So here, according to the common notation, we can say, okay, beta hat is actually equal to the generalized inverse of x. Suppose x star is generalized inverse of x, y plus I minus x star x equal to times z. And in this way, this we can call the generalized the solution of the general solution of this equation. Okay, now we go to the R codes.